Welcome to Chapter 6 for Aquinas Physics Without Calculus. Today we'll be discussing uniform circular motion and gravitation. As always, I bounce between the OpenStax provided slideshows as shown here and the text itself. I will be doing selected questions from the text in depth. And if you have any questions, feel free to comment, email me. This is, of course, not your only source for information on this. Feel free to go to any other source you want to if you have any questions. And of course, always ask me anything you need, right? So with all that, let's begin talking about uniform circular motion. Uniform circular motion is the feeling you get when you go around a corner in a car. That's the easiest way to describe it, right? There are equations and math surrounding this, as every other chapter we've been talking about has. I would argue, as I have previously, that the math is not necessarily difficult. It's more so that it's rearranging things in ways you're probably not used to seeing. That's how this has been progressing, right? We've been doing like division over and over again, but in more and more intricate ways. The way we describe circular motion and motion around shapes like that is we describe it in terms of arc lengths, right? I think the book actually has a better picture explaining this than what's on the slideshow. Yeah, this one here. Actually, no, it's this next slide. Okay, there we go. Your arc length, or your delta S, is shown here. It's described as essentially going around that circle, like going on the outside of the rim. The outside of the tire, the tread of the tire, however long it takes you to pass the tread of that tire is your arc length. And it's defined, of course, by your delta theta down at the center of the angle, which is where the spread begins. So the larger the delta theta, by definition, the larger the delta S at the end. The arc length is defined by the angle, and it's also defined by the radius R shown there, right? So a larger tire will have a larger arc length for a, by comparison, smaller angle. When you see a plane flying overhead, right? The plane itself looks to be moving slowly through the air, but the plane is going 500, 600, 700 miles an hour, right? The plane is moving super, super fast. But since the distance is so great, the radius is so great between you and the plane's arc length, where the plane is traveling, is very, very long, but the angle you're making as you watch it travel is very, very short. So that's kind of the difference we're talking about here. The equation describing these is shown below, and it's also worth noting here, this picture, I think, again, does a good job explaining this, that arc length is not necessarily a straight line on the sphere in reference to the sphere, right? So when that plane, I'll go that example again, the plane flying overhead, if it's keeping a constant altitude above the planet, is actually flying in an arc around the rotation of the planet. So that's one of those nuances to keep in mind. But the arc length distance, its actual distance, is still described by that simple equation because its distance appears to be straight even though it's bending around the corner. And whatever radius you have from the center, that is the key proportion to your arc length. So you can travel the same degrees around a circle, but how far you are away from the center dictates your arc length, and also dictates, as we'll get into here in a bit, centripetal force and centripetal acceleration. Again, the classic example of this is a merry-go-round. You used to play on them at playgrounds all the time, right? And if you at the center of the merry-go-round, when it's going in a circle, that's fine, right? You don't really feel that sick. But when you're on the outside of the merry-go-round and it's going around in a circle, you get flung off and land in the grass and have a good old time, right? That difference is directly related to the radius, how far away you are from the center, not explicitly dictated by the angle being made or the speed going around. But the larger the angle or the faster the speed, obviously, the more arc length you're going to cover and the faster you're going to go around it. Again, notice the equations, they're the exact same. Relating all these instances together is where it can get kind of tricky. We'll go through a couple of those things. Here we have again, practical examples, the gosh, I can't remember that what that W is caught off the top of my head, but these equations here reference the static view of what you're talking about. And if the thing is in motion, say you have a velocity, you apply the same rules here, just you have the thing going around a time, a velocity. So the total velocity of something moving has an angular velocity in proportion to how big the tire is. In essence, right? Your W, what is that? It's not omega. Is it omega? No, I don't think it's omega. The velocity defined by, again, this car is proportional to the radius of the tire and how fast the tire is going around. A smaller tire goes around faster, a larger tire goes around slower. But the total velocity may be the same, just the tires are going different speeds. That's how gearing works, right? That's how transmissions work. That's why we don't have little tiny shopping cart wheels on our cars, because shopping cart wheels need to spin around a lot faster to go the same speed. Again, shown here, the same exact example, comparing the velocity of these flies on a record to the angular velocity, the W looking symbol, and the radius of what we're dealing with. My kid's having a good time in the background. I apologize if you hear that. Okay, so as stated many times before, right, a delta is that triangle there. Delta is a change in. So if you have some sort of difference regarding how fast you're going around those circles, you do have a change. That change is recorded by that delta V. V2 minus V1 equals delta V. That's the exact same as we talked about before. The change that we have, that delta V, relates to the acceleration. And if the acceleration is going around a circle, we call that centripetal acceleration. So all these things prior, this is more of a displacement conversation. This is a velocity. This is an acceleration. You're still having the same basic idea behind the equation, right? Your acceleration, you change your velocity over time, and your velocity, you change in distance over time, right? But now you have to picture things on a circle rather than picture things on a line. That's the big difference. And when we get to the examples as shown here, you'll see that again, when you take the time and find your equations and do your math, they end up not being super difficult to do. So here are the examples of some of the equations we're dealing with here. And when you look at the equations, make sure again to note what the variables mean, right? Delta V means velocity and change of velocity. S and delta S is arc length, so how wide around the tread of the tire, for example. And R, of course, is your radius. So you can solve back and forth for whatever you need to answer your questions. Your centrifugal acceleration is given by your velocity squared over R, because you can note out your delta V's given, again, 614 and 615, the math shown there. So here's your equation. If you need to care about specifics like delta V's, pop up a little bit. Cool. So, and again, we have an equation related to velocity and an equation related to angular velocity. The W there is your angular velocity dictated by the equation we talked about earlier here. Total velocity, you can reference acceleration with regards to velocity or angular velocity because they're kind of describing the same thing and they're related to each other, again, as shown here. How fast the tire is going around is related to how fast the tire is actually moving. So let's do an example real quick. How does the subtripetal acceleration of a car around a curve compared to that due to gravity? So when you go on a curve, you kind of feel like you're being pushed into the side of the car, right? You slide across the seat. What is that in reference to, say, gravity pulling you in a certain direction? So you have a car following a curve of radius 500 meters at a speed of 25 meters per second, 90 kilometers per hour. Compare the acceleration due to gravity for this fairly gentle curve taken at highway speeds. So how do these things relate to each other? Well, what is gravity? Gravity is an acceleration, right? 9.8 meters per second squared. So we need to find the acceleration around the corner and compare that to gravity at a similar pace. All right. So how do we determine acceleration? Well, we're going around a corner. We know the radius of the corner is 500 meters. And we know the velocity that we're traveling, which is 25 meters per second. Okay. So I was given two equations for acceleration around a circle. V squared over R and R, I think it's omega, I want to say squared. Which of those two is more viable for this question? Well, I don't know how fast the tires are moving, but I know how fast the car is moving, right? V describes how fast the car is moving. Omega describes how fast the tires are moving. V is your velocity. Omega is your angular velocity. Well, I think velocity is more useful here, so I'm going to plug that in because I know velocity is 25 meters per second. Square that, divide it by 500, which is my radius given, and I land at about 1.25 meters per second squared. That is the centripetal acceleration caused by going around that corner. What causes that acceleration? We'll get to here in a couple minutes. But when I compare 1.25 to 9.8, which is gravity, the thing that happens to us all the time, we find out that gravity is, in fact, a lot larger, right? This is about, 13% of gravity, which is noticeable, of course. You feel going around the corner, but it's not comparison to gravity at those speeds at that curve, right? It says gentle curve for a reason. As I always dictate, example 6.3 covers a similar conversation here, but I'm not going to go over that. You can go over it yourself if you want to dive a bit deeper into how all these things work. This one actually does conversions from revolutions to meters. That's stuff we covered in chapter 1. I encourage you guys to go look at the textbook. This lecture is not meant to be your sole source of information, right? I say that every time because I mean it. So that is centripetal acceleration, but what is the force being applied? Because we just compared centripetal acceleration to gravity. Gravity is a force that is created by an acceleration due to gravity. So if centripetal acceleration happens, therefore you must have a force involved, right? Well, yeah. So what is that force? I told you earlier that the force you feel is you kind of going into the side of the is this sorry, my kid was going again. The force you feel is the force of you like sliding off to the side, to the outside of the curve, going into the door, right? Well, that's not the force due to going around the circle. It's a bit different, right? And hopefully these pictures kind of explain what we're talking about here. Centripetal force is perpendicular to velocity, and it causes a uniform circular motion. The larger the force going around there, the curve, the larger the force, the smaller the radius of the curvature and the sharper the curve. So if you're going around a very sharp corner, you can have a very large force. If you're going on a very wide corner, you have a very small force, right? And this is also, of course, tied into velocity as the equation showed previously. Noteworthy here is that you notice the red line is pushing towards the center. The force is pushing towards the center of the curve, not away. You feel like you're flying outside of the curve, but the force itself is actually going inside. Well, what does that mean? When we get to fictitious forces, we can go a bit deeper into that conversation. It's interesting, right? These forces that we're talking about here play a big role in the natural world around us. The classic example is always a car going down the road, right? The centripetal force causing a car to turn in a circular path is due to the friction between the tires and the road. So what's pulling the car around the corner is its tires. If you have, you're driving on a wet road, you take a corner too fast, you crash your car, right? So you got to try to picture in your head here real quick, going around a corner, your tires are good and you're sticking to the road, so you're keeping the corner. You're essentially driving your force vector in and around the way that you're going. So how do you take the corner? Well, something needs to push you in that direction, right? A force is a push or a pull. Something pushes you around the corner, if you're taking that, say you're taking a left, right? You're taking that left, you can kind of visualize it as friction pushing to the left. And what is left as you go in the corner? Left is pointing towards the inside of the sphere, which is what's being shown here. Centripetal force, force going on a circle, is force towards the center of the circle. Since we define force as pushes and pulls, it is essentially pushing you towards or pulling you towards the center, which allows you to actually take the corner, because you need to have something making you turn. Newton's first law of motion, right? Object in motion will stay motionless, acted upon by an outside force. When you're taking that corner, something's pushing you in that direction. That push is that centripetal force, and that centripetal force, again, here, comes from something like your tires gripping the pavement. If you don't have that centripetal force from the tires gripping the pavement, you don't take the corner, you go straight in ahead, because there's no force pushing you in towards the corner. It's convoluted, but it allows, this rationale allows us to do the math behind it in a simple way using things like, again, free body diagrams. So let's do one, right? 6.5. What is the ideal speed to take a steeply banked tight curve? Curves on some test tracks and race courses, such as the famous Daytona International Speedway in Florida, are very steeply banked. This banking, with the aid of tire friction and very stable car configurations, allow curves to be taken at very high speeds. To illustrate, calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. So, frictionless means, right, no friction. How fast can you go around a 100-meter curve at 65 degrees if the road isn't giving you anything, right? Slick road, essentially. So let's take this information, figure out our terms, and move on from there. We're talking about banking here. So let's take a look at this image here, right? We have a theta involved, which is something we didn't talk about before. That theta relates our weight to our normal value, right? What's that? Not polygonal. I'm losing the word. Oh no. If this theta down here at the bottom is equal to this theta up here in the blue car, polygram, whatever. You're familiar. I'm sure you're familiar with that. I'm forgetting the name of the rule off the top of my head. But since these thetas are the same, we can cosine and sine out the forces associated with that normal and that weight force, and that will tell us a bit. That'll give us information that we can then throw back into our circular notational equations that we talked about in the previous chapters to solve our problems. So the sine of that theta times the normal force gives us the force pushing in to the left, right? The x value. And the cosine of that n gives us a weight value. So we can get our centripetal force keeping us on the track from our x force pushing us in, making us go around the corner. Because if it wasn't pushing us in, we wouldn't be turning in. If we weren't turning in, we'd be going straight. Right? So we can start. Oh, sorry, I stepped a bit ahead there. We have our sine and we have our cosine. And we also have the equations relating how they work together, right? So what we can do is we can use the sine and the cosine and their subsequent relations to weight and net force to the left, and we can actually combine them because weight is mass times gravity, right? And the sine here is the centripetal motion, which is related to our velocity squared over r. We're going to throw mass in there as well because we're dealing with an acceleration, right? F equals ma. The acceleration is our velocity squared over r, and our mass is m. So the force along the centripetal motion of the x is n sine theta. F equals ma. And the force down is n cosine theta equals mg. So I can combine all of these things to land on an equation relating the forces together. Essentially, I'm going to take my n's, I'm going to set them equal to each other, right? So I have n equals mv over r. Sorry, I have and I'm going to throw the sign on the bottom here and the cosine on the bottom there. I'm going to rearrange the equations to solve for n. This sentence right here in the center shows what I'm talking about. And I can land on something that kind of gets rid of a lot of stuff I don't care about and gives me information I want. Namely, I can find an equation relating the angle to the amount of centripetal force given by that angle at a speed, which is what's shown here. This equation, 6.36, says the banking of the theta alone provides this much centripetal force. So I take that equation and I want to know the speed at which I can go around this corner, given a 100-meter radius and 65 degrees. And I put in the stuff I know. I know my radius, I know gravity, I know my degree, and I can solve it out about 45 meters per second, which, think back to what we talked about before, is pretty fast. I think it was the previous question had that going someplace 90, 100 kilometers per hour, which is impressive, right? A frictionless road, bank that degree, gives you like 100 kilometers per hour turn. There's a lot of power in this centripetal force. There's a lot of power pushing the car in towards the center to allow it to take the corner simply by the angle of it and gravity essentially being your engine. Like 165, I was even off there. 165 with a frictionless corner. So the car's NASCAR, for example, goes much faster, goes even faster than that if it wants to, because tires are very wide and very sticky, right? So yeah, we're starting to enter the point to, I keep saying the math is easy, but we are starting to have to like create equations to solve what you need to solve here. And that can get tricky. I get that. But if we take the time, the book does a very decent job of outlining each equation. And I would argue explaining the reasons why we combine them the way we combine them. And take a little bit of that intuition, right? You say, okay, 6.34, how did we get to 6.34? Well, 6.33 and 6.32 have a lot of similar variables, but 6.34 doesn't have an n. Why is that? Right? I think you can, you get where you need to go at that point. At least I hope you will. There was that centripetal force. That is the force pushing you towards the center of what you're going around. But as I said previously, you feel like you're being thrown out of the car when you go on a sharp corner, right? Like you're shoved against the door. Why is that? You shoved against the door because of a fictitious force that you tend to be heard called, what's it called again? Centrifugal. Centrifugal force is essentially the fictitious opposite of centrifugal force. Centripetal force. Centrifugal force, highlighted here, is the force you think you're feeling, and centripetal force is the force that's actually happening. Okay? What do I mean by that? Centripetal force is the thing that we've talked about this a lot, is having you go around the corners. That force from the outside pushing in, or if you will, the force of whatever is holding you to the road, keeping you on the road. But when you do that, the car, for example, is taking the corner, but you're not the car, right? You're a person in the car. So inertia, we've talked about that a bit before. Inertia says, I want to keep going the way I'm going. Newton's first law of motion, a object in motion will stay in motion and stay in the same motion, I should add, and that's acted upon by an outside force. If you crash your car, you're not wearing a seatbelt, what happens? The car stops, you keep flying out the window, right? Because your body wants to keep going the way it keeps going until it splats against a tree. If you go around a corner, you want to keep going straight, even though the car wants to turn. So that force that feels like it's pushing you out is actually your inertia wanting to go in the same direction. when you're going on a merry-go-round, if you take a snapshot at each of those moments, we talked about this before with the snapshots of projectile motion, right? You take a snapshot at any given moment, you have a velocity perpendicular to the rotation of the merry-go-round. The reason you go around the corner is because you're gripping the merry-go-round, and the force of you gripping the merry-go-round is dragging you in a circle. If you let go of the merry-go-round, you fly off of it because you want to keep going straight at that snapshot. That is centripetal motion, is your hands gripping going around, and centrifugal motion, the fictitious motion, is the want to fly off. There's nothing actually pulling you off. It's inertia, which is the lack of a force that's throwing you off. That all being said, we can use this idea of inertia to do stuff, funny enough, right? Things such as centrifuges, right? That spin and separate out materials based on density. They use this basic concept. Merry-go-rounds, of course, we talked about that a lot, right? And notice here, I'm not bringing up a bunch of different equations. I'm going over a concept here. Coriolis is an example of this perceived force causing motions. Coriolis, of course, reflects the rotation of the Earth, right? And all of these things are following centripetal motion, following circular equations, but the result of following the equations looks like something that's not, right? A merry-go-round looks like and feels like it's trying to send you off outside of it, when in reality it's trying to pull you in. It's confusing, I get it. When you get a second, go outside, do a merry-go-round, and play. And you're gonna notice real quick the difference between centripetal and centrifugal motion. So that was all covered there. Cool. Let's move on to law of gravity. A good obvious example of circular motion in a way that's not like always talking about tires and cars is gravity and orbit, right? The moon orbits around the Earth orbits around the sun. Why? Well, because, and it's also a good example of what centripetal motion is, the moon orbits around the Earth because the Earth is heavier than it and has a gravitational pull that the moon is fueling, right? When you jump up in the air, what pulls you back down is gravity. We talked about gravity previously, 9.8 meters per second squared, right? But if you're going in a circle, if you have a speed outside of that, like a projectile motion, for example, you want to be pulled in, but your inertia wants you to go out. And the fight between gravity pulling you in and your inertia pulling you out causes you to have an orbit. That is what the moon is doing. The moon is going fast enough that it can fight the inward pull of the Earth, and the Earth is strong enough that it can fight the outward push of the moon. This picture right here. And the relation between gravity is actually described by Newton. Sound familiar, right? He did a lot. As this equation right here. The force of gravity equals a gravitational constant times the mass of each object multiplied by themselves over the radius between the two squared. And cool little concept here, similar to Newton's third law of motion, the equal and opposite forces, gravity impacts both things equally. So the pull that the Earth is imparting on the moon is equal to the pull the moon is imparting on the Earth. It's just one's bigger than the other, so they are affected differently. The further away you get from the Earth, the less gravity, and therefore the more centripetal motion, as we've already talked about. And let's do an example of what we're saying here. So some numbers on top of it, right? So 6.6, right? Yep, 6.6. Earth's gravitational force is centripetal force, making the moon move. Wow, in a curved path. Find its acceleration due to Earth's gravity at the distance of the moon. and then calculate the centripetal acceleration. So first of all, find the linear acceleration, and then calculate the centripetal acceleration needed to keep the moon in its orbit, assuming a perfect circular orbit on a fixed Earth, and compare that with the value of the acceleration due to Earth's gravity that you just found. And of course, you're going to need to know a couple things here. Big one, moon's radius is 3.84 times 10 to the 8th meters. Moon's a long distance away. So what is the gravity felt? What gravity is pulling on the moon by the Earth? Well, the gravity pulling the moon by the Earth is given by this equation here, right? The one that I talked about. Unless you get into like astrophysics, you're not going to need to memorize the gravitational constant. You can just go back to it, but there it is right there. 6.674 times 10 to the negative 11th Newton meter squared per kilogram squared. Just rolls off the tongue, right? So we can substitute known values into the expression G found above that we talked about, remembering that one of the masses is the mass of the Earth and not the moon. So if we know the mass of the Earth and we know how far away it is, how much gravity is being exerted that far away? Because I'm looking at this from a one-dimensional thing. How much gravitational force is something a moon's distance away feeling? Well, we take a gravitational constant, right? And we plug in the mass of the Earth, which is 5.98 times 10 to the 4th kilograms. And we divide that by said radius squared to get a total gravitational force and acceleration of 2.7 times 10 to the negative 3rd meters per second squared. A lot smaller than 9.8, right? A lot smaller. That's almost 4 magnitudes smaller. So how does that number compare to, as said here, the centripetal acceleration that keeps moon in its orbit? So in order to know the centripetal acceleration, we need to look at the equations that we have. Centripetal acceleration is given to us by v squared over r, or given to us by r omega squared. Which of these two is more useful? Well, I don't know how fast the moon is moving, but I can figure out how fast it's going around a circle, right? I know my acceleration, and I know my radius, so I can solve that. So what do I need here? Well, how do I figure out my centripetal velocity, my omega here, my weird looking W? Well, velocity is displacement over time. So if I can figure out how big the moon's orbit is, how long it takes to do it, I thereby have my velocity. And that was given to us right way, way, way at the top there, right? Where you at? There it is, right? Velocity equals delta S over delta T, or delta omega over delta T, whichever you have access to, right? So go back to 6.5. So notice here I'm jumping back and forth between chapters to find the answers and find the equations I need to do. This is what I highly encourage you to do. It's a good skill to have, knowing where to find your answers. So given the period, again, something you need to be told, right? The period, or the amount of time it takes the moon to orbit, is 27.3 days. I can convert that into SI units, which are seconds. And then I can throw in my needed information. What is my change in angle for one complete orbit? Well, it's one complete orbit. It's 360 degrees or 2 pi radians. We're going to go with radians here because a lot of this stuff takes place in radians, right? Your centripetal acceleration, we tend to think of as radians. Didn't go over that too much at the beginning because it kind of depends on the question you're asking. You can do this in degrees too if you want. But if we take 2 pi rads and we divide that out by the time we talked about before, we can land on a total centripetal acceleration. A centripetal velocity in omega for going around that circle. And what we find is that the centripetal velocity is 2.66 times 10 to the 6 rads per second, or radians per second. So throw that back into our acceleration, and we land on a centripetal acceleration of the moon going around in that circle of 2.72 times 10 to the negative 3rd meters per second. How do these two relate to each other? Well, Earth is pulling in at 2.70 times 10 negative third, and the moon is essentially flying away at 2.72 times 10 negative third. Very, 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 very close to each other, right? It's almost a 1-to-1. But the moon is moving away from the Earth ever so slightly by two 1/100ths of a 10 to the negative third meter per second, right? The moon is leaving us very, 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 very slowly because the moon essentially is moving too fast. So there you go. Example of the action in play. And of course, the reality of the situation, the moon is in a perfect circle, the Earth is moving too. So, you do have particles and friction in space that barely even count. Asteroids can throw this stuff off, right? But anyways, this motion of the moon, of course, pulls tides high and low. You probably learned about this stuff in Earth science class back in high school. So I'm not going to go too depth into it now. But these tides play a big part in the wobble of the Earth and stuff like that, and alignments with the moon and what have you. All the equations we're talking about here play a big role in kind of all of astronomy. You have these real cool, like, black holes bleeding stars off, creating these wonderful orbits and stuff like that. When we look out in space, we see things following Newton's law of gravity, which is just bonkers, right? Newton was around in what, the late 16, early 1700s, and he derived an equation that, in rather simple terms, explains things he never actually saw. That's pretty impressive, right? These sort of conversations go into feelings like weightlessness and stuff like that, right? When I talked about before a car going around a circle, I said that the feeling of you not being the car as the car goes on a circle causes that motion out to the side to hitting the door. When you're weightless, everything is disconnected. There's no forces affecting anything. So the reason why you can walk on the ground here and you have a weight is because gravity is pulling you down. If you don't have gravity pulling you down anymore, you have no forces, nothing's impacting you. So that's the idea of weightlessness. When you see a high quality sci-fi movie and a space station, the space station's always moving, right? 2001 Space Odyssey, space station's always moving. Space station's always moving because that centripetal acceleration created the pulling you down motion of it, fakes a gravity and allows these things to exist. And this is like a real thing out there. If you spin a space station up in space, the motion of the inertia pushing the astronauts out towards the side is itself a version of gravity, right? That's pretty cool stuff. This is a bit of a Cavendish's experiment. This actually, I think, was disproving the aether and showing that, and ended up showing that, well, gravity is a thing that causes things to orbit and all that jazz. You can read about it in the book if you want. It's pretty cool stuff. Here's a bit about Kepler. Again, kind of more of applications of these centripetal motions and gravity and understanding how the universe functions. I want to get to the equation here at 6.6. There we go. So yeah, the math that we're talking about now, in essence, expanded the understanding of the physical sciences and created was the foundational aspect that went on to create biology, geology, physics, all that jazz, right? The stars, understanding that you could write down on a piece of paper some equations, and that's actually how, like, the star moved and planets moved and stuff like that, right? That was the inception of what we call science in a modern day. Super interesting stuff. 6.6. Oh, 6.6 here. Look at. Oh, there it is. Okay, I rolled right by it. Sorry. Earth's gravitational force is centripetal force making the move. Oh, we already did this. Okay. So that is presentation. A lot of this conversation revolves on, again, those few equations at the start, namely your centripetal force motion. Here, your centripetal acceleration is a big part of it right here. And this is also connected to your rotational acceleration and your rotational velocity shown here. Connecting these equations, I keep throwing new Greek letters at you, like omegas. Try to keep track of it. It can be a bit daunting sometimes, but taking your time, going through things slowly, not trying to rush your homework together over a weekend will help you solve these problems. Let me know if you have any questions. Take care.